Quantum computers promise to revolutionize a vast range of sectors important to our everyday lives. However, current generation quantum computers are proof-of-principle devices with just a handful of qubits, which act as the information carriers in a quantum processor.
My team developed silicon quantum computing based on the same technology used to manufacture the silicon chips used for existing IT. In recent years, we've jumped a number of important hurdles on the pathway to building a full-scale quantum computer. However, in the back of my mind, there's always been this nagging question of how we're going to go from controlling just a few qubits, which we can do now, to controlling the millions of qubits that are going to be needed to harness the full potential of quantum computing. Then last year, Jared came to me with a brilliant solution to the problem.
In one of our recent experiments carried out by PhD students Ensar and James, we believe we found a solution to this very challenging problem, capable of delivering control signals to millions of qubits simultaneously. In silicon quantum processors, information is stored in the spin of individual electrons, which sit beneath tiny metallic electrodes at the chip surface. In order to write information to the spin qubits, we send a fast oscillating current down a wire that's fabricated on the chip. This current generates an oscillating magnetic field that causes the qubits to rotate and allows us to control their state. The issue with using this technique to deliver the control field is that it's highly localized to the current carrying wire, which means it's only effective at controlling qubits close to it. As we move away from the wire, the speed of the qubit rotations is reduced. Scaling up to millions of qubits, we would require many wires, which would generate too much heat and take up valuable chip real estate. In our new result, we have removed the control wire and come up with a new way to deliver the field that can cover the entire quantum chip. We place a small crystal on top of the device and excite it with low-power microwaves. The crystal resonates and produces a uniform magnetic control field across an area on the chip capable of reaching several million qubits. Since this field is uniform, the qubits all rotate at similar speeds, which is critical for improving reliability and avoiding errors.
I'm really excited by the possibilities that this new technique opens up, because it was the missing piece of the puzzle. There's still lots of engineering to be done to reliably manufacture millions of qubits that are going to be needed in the future, but this now shows us a way of controlling those millions.
Quantum computing technology really has the potential to affect lives. This result gets us one step closer to realizing all this potential.